Hello, everyone. Thank you for joining us today. Today, the GeoCue team will overview and compare our TrueView 3D imaging sensors, including the TrueView 410, the 515, the 635, and the 640, along with how to evaluate which system best fits your drone mapping project needs. Before we get started, I would like to go ahead and do an audio check. Please notice the raise your hand button has been circled and red on the slide. If you can hear me, please click this button now. And we've still got people joining us, so I'll give everybody a few seconds to click those circle or those hands. Great. Awesome. Looks like everybody can hear me. My name is Crystal Bailey, and I will be moderating today's session. Joining me today is GeoCue's President and CTO, Lewis Graham, Senior Business Consultant, Madeline McNabb, and our VP of Special Projects, Martin Flood, who will be answering questions during the webinar. Before we begin, I would like to go over a few things. Group audio has been disabled for this session. If you would like to ask a question, please use the question box on your GoToWebinar panel. This session will be roughly 60 minutes. If we do not get to your question during this webinar, we will follow up with you by email. This webinar is being recorded and will be distributed to everyone registered. Now at this time, I will be launching one poll question to get us started. Please indicate your use of drone mapping/inspection technology. Check all that apply. I'll leave this open. This is just going to give us a good idea of the user group with us today, and I will share these results with everybody once it's completed. Leave this open for just a little bit longer. We're still getting votes in. All right. We'll go ahead and close that poll and share those results with everybody. All right, so it looks like we got a fair amount doing photogrammetric mapping using drones and LiDAR and photogrammetric mapping with drones. That's awesome. Well, thank you for voting. Joining me now is GeoCue's President and CTO, Mr. Lewis Graham, and I will hand over the presentation to him now.
Thanks, Crystal. Can you see my screen okay now?
Yep, I can see it and hear you perfectly.
Thank you. Well, good morning. Well, if you're in our time zone, good morning to everyone. Thanks a lot for taking some of your time to have a look at our TrueView 3D imaging sensors. This is a kind of a top-level overview of the range of products that are within the family right now. It's not really aimed to talk about, what sorts of parameters you would look for in an airborne laser scan or so forth. We do plan on doing that probably as our next webinar. It's one we did maybe 6 months ago and people enjoyed it. And it'll talk about the details of what you should look for in technical specs on the laser. All right, slides to advance. So quickly about our company, we were founded in 2003, so we've been around for quite some time. Our focus has been on various aspects of laser scanning since we started. Our headquarters is in Huntsville, Alabama. We've got an office in Toronto, Canada, and also in Brisbane, Australia. We're still privately owned. And our focus, again, has been on LiDAR and imaging technology. We do three different major things within the company. So on the left is our airborne and mobile laser scanning solutions. Here we focus on software and training for manned mobile vehicles and aircraft. So TerraSolid processing, LP360, that sort of thing. And on the right-hand side is enterprise solutions. So we do custom development based these days primarily around applications built in Amazon Web Services. And then the thing that you're here for, our drone mapping, has become about 44% of our business. And we've got end-to-end workflow solutions, both sensors and software. We focus very much on the survey part of the industry. We don't really do much in inspection, that sort of thing, but mostly on surveying and mapping. So we've done well over 3,500 drone mapping projects since we started into the drone business around 2012. These are all metric managed or metric accuracy measured projects where we put out ground control and we measure the results of what we're doing. We've collected quite a few customers into our portfolio in the drone mapping arena. Here's an example of a few of those. You can see they're scattered around North America, Australia, Africa. So with that, let's launch right into the sensors. So 3D imaging sensors, from the beginning when we started building our own LiDAR sensors, we wanted to add camera technology directly mated with the LiDAR system so that we could have direct fusion of image data and LiDAR data in post-processing. So it's really important to us. We realized that point clouds are nice, and here you have a typical point cloud from a drone laser scanner. This happens to be a TrueView 515. Colored by elevation, so you're used to seeing this kind of visualization. But if we add color from the RGB cameras directly into the point cloud, this really changes your ability to perceive what's in the project, your ability to extract features and so forth. It's really, well, it's even bigger than the difference between black and white imagery and color imagery. Here we have a side-by-side, color by elevation on the left, which is typical from a LiDAR system immediately after post-processing, versus the right, where you see this colorized, same exact scene, but now color added from the RGB cameras. So pretty difficult. You get a vague notion in the left-hand image of what's going on, but certainly in the right-hand image, you immediately say, I see that's a gravel blanketed drainage ditch. So we built these systems, we built a range. We've now got a pretty complete portfolio ranging from the survey grade 635, 640 down to the general purpose TrueView 410. So let's go into those and look at some of the motivation behind building them and what's the difference between these sensors. So when we started this out, we wanted to have a range of sensors that covered, general purpose topographic mapping where 1 foot contour and vegetated areas is what I'm after, all the way up to survey grade where perhaps I'm doing a highway cross sections where I need high precision, high accuracy. It was very important to have standard workflow outputs with this. So we wanted to be able to do fusion by design. So this means you don't go generate an orthophoto and then colorize LiDAR from that orthophoto, but it's actually fused through a ray tracing process. And we'll talk a little bit more about that as we go on. But that puts some hardware constraints on our system because you need an extremely well calibrated platform in order to do this. We wanted to have our core technology to have some growth room, so enough processing power that we could handle the range of systems and so forth. And then another thing that we wanted in the design was to be independent of the drone from an electrical and signal point of view. So you can go put TrueView 3D imaging sensors on any drone that's capable of carrying the payload. So in this family of sensors from the 410 to the 635, 640, they're all of the same basic design. And here you see the layout of that sensor. So we have the characteristics of our laser scanner. In this case, it's the Regal Minivux 3. Dual cameras. So these cameras are offset by 25 degrees from nadir. That gives us a total 120 degree field of view. So that's really nice because we can colorize the full usable swath of the LiDAR with single pass photography. And those of you who are flying systems now like DLSR cameras attached to LiDAR systems, this is a big benefit that you don't have to do separate flights for photography and laser scanning. And then we've got all of the electronics housed in the electronics housing. In all of our systems, we use a Planix positioning, either APX15 or the APX20. And all of this is coupled together on a rigid frame. And again, this is so that we can maintain a high level of calibration in the sensor. Just an example of a TrueView 515 mounted on an M300 drone. So the 410 and the 515 can be carried on the new M300 platform. So the thing that differentiates the 3D imaging sensors in our TrueView 3DIS portfolio is the type of laser scanner that we use. So we did a lot of research into various kinds of laser scanners, ranging from the very low end Livox sensors up through Velodyne, and then at the high end, the Regal systems. And we selected 3 sensors that really represent the range of capabilities that we see out in the marketplace today. So the everyday all-purpose sensor is the Quanergy M8 Ultra. We've had this, this was the first system that we built into the TrueView 410. Excellent general purpose scanner for day-to-day topographic mapping, volumetrics, and those kinds of activities. On the high end, we have the TrueView 635, 640. So this is based on the new Regal Minivux 3, where you can get high pulse repetition rate in 120-degree field of view. So it's very interesting that the field of view for high pulse repetition rate for the Regal exactly matches our camera configuration. And then recently we've added the Hesai Pandar X32 to this product range, and this was really designed to be a lower cost system that could do wire extraction and dense vegetation. So this is a 32 beam scanner that really gets a lot of points on the ground. We'll look at the difference between these a little bit later on. We have a custom designed camera that we use with the system called the GeoCue mapping camera. So this camera was built for us for integration into our 3D imaging systems. It's a 20 megapixel RGB camera that uses a mechanical shutter, which is something you have to have for photogrammetric mapping. And it also has electronic trigger, so it tells our electronics unit exactly when the image was taken so that we can synchronize it with the Applanix position orientation system. And this is really one of the keys to being able to do direct rendering of the point cloud with the RGB data. We calibrate all of these cameras in a precise calibration process. And again, another key to being able to successfully have high accuracy data and to do data fusion is to have a real rigid platform for all of the components. So we use aluminum milled machined parts. Everything is precisely fitted. We do several calibration flights with the systems after they're manufactured, and that really dials in, so we build our systems to say 25 degrees off nadir, and then we calibrate it down to what it may truly be, like 24.937, etc. We have a separate control unit that mounts on top of the drone, so this removes the need to peer underneath the drone to try to figure out what's going on. In an update since the initial controller for the TrueView 410, we've added a LCD readout, so you can now get status messages as the system goes through its various boot up and wind down configurations. And as was stated earlier, we use Applanix APX systems for position orientation in all 3 of the products within the product family. We did a lot of evaluation on this before it was selected. We've worked with Applanix and other companies since the 1990s. They're the world leader, I think, in position orientation for this kind of survey and mapping technology. And we use both the APX 15, this is for the general purpose systems, high accuracy and XYZ pitch and roll. And when you need to improve accuracy in the heading dimension, then an external IMU, inertial measurement unit, the IMU 82, can be added onto the system. This really improves the heading response of the position orientation system. So I'll talk about this just a minute because we get questions about what's the difference between a TrueView 635 and a TrueView 640, and it really primarily has to do with improved heading available from the orientation unit. So heading is the direction that the craft is pointed as it goes down a trajectory line. And it's not necessarily the course over ground because the system is yawed due to wind and other factors. There aren't accelerations along this dimension unless you purposefully accelerate the vehicle. And so this is the attribute or the position vector that's most difficult to compute. So let's see what the difference between the APX-15 and the APX-20 is. So what we did is that we did some test flights, and then we used a photogrammetric block bundle adjustment to figure out what the heading of the system actually was, and we compared that to the heading that we read from the Atlantic system. So here in this lower chart, you can see the blue is the heading for each flight line from the APX-15. And you see it's actually quite good. You know, excursions are within a reasonable range, so not too large. But when you add in the APX-20 external IMU, you can see this really improves the heading accuracy or the pointing accuracy of the position orientation unit. It really drives this down. That becomes important when you're looking off nadir or off directly downward. So you're looking at, say, collecting vertical objects like towers and power poles and that sort of thing that are at oblique angles from the sensor. So if we look at you might call a decision matrix on which of these sensors is appropriate for the kind of work that you do, we've gone from visualization all the way down to what I call Department of Transportation expectations. And for the most part, departments of transportation expect Regals, and so I say down here that's what you pick. I won't go over these in detail, but it looks at the general kinds of application areas that in which you might be involved. If you've got things that need to be added to this, it's certainly a work in progress. Just shoot me an email and we'll map those into this matrix. So processing software is critically important to success in this business. So just the hardware is just, you know, half the story. You've really got to have a really good post-processing workflow to make the data into something that is accurate and is useful for the kinds of applications that you're involved in. So we've got a complete, what I call ecosystem built around the TrueView systems that comprise desktop software, some web applications where those web applications are appropriate, and a product that we call TrueView Reckon. So the desktop is TrueView Evo, TrueView Reckon is our cloud solution, and then backing this up is software from Applanix called POSPAC, which is used for processing the position orientation data. So the software, the complete post-processing software is included with every system, whether you have one of our 410 or 515s under a subscription system or you've purchased the system. You always get the complete stack of software, and that's really important. You know, you don't want to buy a laser scanner and the vendor of the laser scanner says, well, you know, we take it up to the point that you've got an elevation model. If you want to do anything else, go buy XYZ software. You know, then you're kind of into an integrate it yourself situation. Some of you may like that challenge. Most of you like to just get things up and running and get out and collect data. So here's a typical workflow from mission planning all the way to analytic product output from the workflow. You know, are you going to go, what is it you're going to do? Volumetric analysis, generate DEMS, cross sections, and that sort of thing. And the things that are in green are included within TrueView Evo. So in a typical workflow, what we have found most customers want is the ability to generate an orthomosaic, a photo orthomosaic from the imagery. And here we recommend third-party software such as Agisoft Metashape, which is directly integrated with TrueView Evo, or you can use Pix4D context capture applications such as those other photogrammetric routines. So as we step through this workflow, it starts with a nice, easy to use import wizard that allows you to bring in what we call a cycle. So this is a flight of the sensor. The data is transferred from the sensor to the application on the workstation just using a USB memory stick. Plug that into your computer and run this wizard and start the import process. So you can do a couple of things at the import stage. You can say, well, I don't want to process right now. I just want to archive this data. You can archive it locally. You can archive it to a local server on your own internal network, or you can push it up to Reckon in the cloud and store it in Amazon Web Services. So you've got some options at this stage. But if you're going to process, as soon as the data is imported from the USB, you get a nice graphic of what was flown. So you get a WMS background if you have web connectivity. So this is the map that you see in the background on this image. And you see the flight path at 1 second intervals of exactly what it is that you flew. So this is really nice even to use as field check, because you see that, yes, I flew what I intended to fly. Things look good. Photos are immediately part of the process. So as soon as you import a project, you can look at individual photos from the cameras, and there's a more valuable way that these are used that I'll talk about in a few minutes. A Planix pause pack can be a bit of an intimidating application, so we've built the controls that you need for pause pack directly into a processing wizard within Evo. Excuse me. So you don't have to exit the application to run pause pack. This too is a wizard, steps you through just a couple of pages of information, most of which is extracted from our project information itself. It gives you a couple of options for processing. So this is really nice because even if you don't have a subscription to Trimble PPRTX, you can run it on a metered basis from within TrueView Evo. That is, just pay for the minutes that you need. That's really handy if you had, for example, a base station failure and now you need a backup way to process the project. Flight lines are automatically laid out, and then we've got automatic tools that will let you go in and clip off the parts of flight lines that you don't want, turnarounds, ferry lines, etc. And that's done through a semi-automated process. Most of the time you can just press a button that says, clip anything shorter than 50 feet, that sort of thing, and quickly get flight lines. The next step in the process is simply geocoding the LiDAR data. So this takes the range data, the information from the position orientation system, etc., and builds a 3D point cloud in LAS format. Now, something we've added here that I think is really valuable is that the calibration data for the sensor is stored in the cloud on TrueView Reckon. So in a just-in-time way, when this dialog runs, it sends a serial number out to the cloud, says, give me back the calibration file. That is the proper one for the date, time, and for this sensor serial number, and that's handed back. So that's really nice because if we need to recalibrate your sensor, we'll have you fly a particular pattern, send us the data, we'll recalibrate. We just post it up to rec, and the next time you fly, you'll get the correct calibration. So when you're done with that, you get a typical, here's a typical color by elevation point cloud from the sensor. But with our 3D imaging system, you have one more step, which is colorizing the LiDAR data from the camera information. When you run that step, you now have a completely colorized RGB point cloud. So this is the standard product from any TrueView 3D imaging system. The entire process takes, perhaps 2/3 of the flight time. So if you had say a 15-minute flight, it would take 10 minutes or less to get post-processed to the point that you have colorized point cloud. Those of you who are doing LiDAR already and are colorizing point clouds from orthophotos, you know that process can take hours because you have to go off to photogrammetry software, generate the orthophoto, then go through a colorization process. But the problem is, even if you do that, you don't get that great of a point cloud. So on the left in this image is a scene captured with a TrueView 515 from 75 meters of altitude, and we're looking at the end of a building. And what we did is we took this point cloud and then we deliberately colorized this point cloud using an orthophoto. And you can see that the problem with orthophoto colorization is that for any XY location, you can only get one particular color. So if you pick any XY location and travel up, you're going to get a single color. Whereas on the right is a point traced colorization, where we take every point in the point cloud, we trace it to the original source image, not to an orthophoto, and we interpret the correct RGB from that source image. So you can see a lot more detail in this image on the right. For example, there's two service doors beside this bay door. They're not even visible in this other image, and that's because it picked the top pixel and colorized the whole vertical streams down the face of this building with that same color. And you can see that very distinct sameness in this vertical extent on the left image, whereas you see all of the detail on this right image. So this bit about how we colorize point clouds in a 3DIS system truly is important, and it really makes a substantial difference uh, in the quality of the colorized point cloud, particularly if you're looking at things like construction scenes where you have a lot of different vertical objects, you know, structures of buildings, overhead cranes, things of that nature. TrueView Evo, unlike a lot of other software, includes a very robust toolkit for what you do after you have colorized point cloud. And typically that's going to be things like low noise, high noise removal, classification of ground surfaces, certainly assessing accuracy, both horizontal and vertical, so forth and so on, all the way through automatic toe generation, volumetric analysis, rail, wire extraction. So just a very robust toolkit contained within TrueView Evo. And then a new bonus that we're just now releasing to market is something we call Evo Explorer. So for those of you who are doing services for your customers, this allows you to provide them a data package as well as a free viewer. They can bring the LiDAR and image data into their viewer through a compressed package called an Explorer package. So the transmission of this package is a single compressed file. Your customer imports it, then they're able to do things like view the colorized point cloud in 3D, as you see over here in the right. But they can also click anywhere in the image, in the 3D point cloud, and it will bring up the images that see that particular point. So here we've clicked on a point in the point cloud, and it brings up the photographs that are seeing that particular object space, and we see there's an umbrella here. So this is really great for construction inspection. So I've got a say a girder that I can see in the colorized LiDAR data, but I want to see if bolts have been placed in that girder or not, so I can bring up the photographs and have a look at that. And then a bonus in Evo is that all copies of Evo from Light and up, and certainly everything that comes with the 3DIS, includes the ability to process in PPK mode data from Phantom 4 RTKs and the M300 RTK with the new P1 camera. So you can process both of those. And we've also enabled Trimble RTX in that workflow. So this Evo software will allow you in a metered way, again, to go use Trimble RTX processing. So that's a nice little bonus. Let's talk quickly about accuracy, precision, sensitivity. So precision, let's see if I put a slide in here. Yeah, I've got it in the wrong order. So precision means if I fire laser shots at a planar surface, at a flat planar surface, how much will those shots deviate from that planar surface? It's also often called noise. So here, let's have a look at it. Starting with the TrueView 635, 640, they both have the same noise characteristics if I'm looking at vertical surfaces, like this is a highway surface. This grid is 10 by 10, and so you can see this characteristic regal data. It's just almost flat as a pancake. So these bits of deviation that we're seeing are really just roughness on the road surface, etc. So just excellent precision out of the Regal sensor. That's why departments of transportation really prefer that Regals be used in their projects. Here's the TrueView 515. So this is a high density scanner aimed at really at wire collection and vegetation in thick vegetated areas. Usually you pay a huge penalty for high point density in the form of noise. And the reason you do that is the very high points density scanners tend to have a lot of channels, at least in UAV type sensors. But here in the Pandar X32, we've certainly got a really nice, a pretty tight noise envelope, and this is multi flight line as well. It's not just a single flight line. And then here we have the TrueView 410. The noise envelope is quite similar to the noise envelope of the 515, and sometimes they'll flip just depending on how well the sensor's been calibrated or how long it's been since the sensor was calibrated. But in all cases, decent noise level. Here's looking at so that was just sort of a qualitative look at it. Let's have a quantitative look at what the numbers actually are. So if you look at the TrueView 640, and what I've done is I've looked at this rectangular patch in green on a highway surface. So this is a bit of a rough, but it is a blacktop road. So we're looking at what kind of precision we're seeing on this road surface. So with the 640, we have a density of 178 points per meter squared, and this is a Regal 3 UAV. So this will give us 200 points per 200,000 points per second in a 120-degree field of view, and that's the mode we were running the sensor in to give us 178 points per meter squared. So more density than you need for any kind of imaginable project. We have a precision at 1 sigma, 1 standard deviation of 1.6 centimeters. That's an extremely quiet sensor. So this is really quite remarkable for an airborne drone sensor. And the total range in this entire area of what we might call noise is only 11 centimeters. That's peak to peak. So this is a very quiet, very low noise sensor. The TrueView 515 on this particular project you can see it's high density at almost 400 points per square meter. So you can see where you get a lot of vegetation penetration. Precision not as good, of course, as the Regal at 3.4, and the range goes up. And then the 410, 275 points per meter squared. So still a high density scanner, precision down to 4.2 centimeters in this case. So what about wire detection for those of you that are out doing wire collection? So here we've flown the 3 scanners at 75 meters above ground level. So the distance from the wires, varies, but they're all under the same exact flight conditions. So here with the TrueView 635, 640 in the top view, you see that, just perfect wire collection. Anywhere you see it fade out a little bit, that's simply the pitch of the drone is causing densification, rarefication in the flight direction. But, obviously more than enough points for collecting catenaries and very low noise, very distinct view of these wires. In the middle is the 515. Here we see even more points on the wires, and of course that's because the 515 is about twice the point density of the Regal system. If you go zoom in on it, you'll see that the noise level with the 515 is a bit higher than the Regal. That's what we would expect, but this is a great sensor for wire collection. You see the sensitivity at 75 meters is great. We're not missing any wires in these bundles. This wire over here that on the left on this pole that looks like it terminates is actually just deviating out of the profile view. It's headed off to a building. Then on the lower image, I've got the TrueView 410. And we've always cautioned our customers about the TrueView 410. If you're going to collect wires with the TrueView 410, and a lot of our customers do, you need to fly it lower. So you need to fly down at about 50 meters. With the 515 and the Regal, no problem. And then let's look at ground detection. Of course, we're always very interested in ground detection in vegetated areas. So we flew all 3 sensors over an area that I call piney woods. It's tall pine trees. That's not the densest vegetation. We admit that. We'll redo this test this summer when we've got much more leaf on deciduous trees and revisit this comparison. But again, all sensors are being compared against each other. So that does give you good relative information. So what I've got is a profile view here that's 10 centimeters wide. And then we also looking at the ground track for each sensor. All 3 sensors were flown at 75 meters above ground level. So here's the 640. You see we've got nice vegetation definition, so we can see the stems, we can see the vegetation on these trees, and really a good good ground penetration along this whole swath. No problem at all generating a DEM. Here's the TrueView 515, and you see this increased point density. So we see a lot more definition within the tree structure, more points on the ground. You probably can't see it in this slide, but you know, it's a more noisy ground than what you see in the Regal, and that's what we would expect. And then finally, the TrueView 410, again, you know, good canopy definition, not as much stem definition, so not much down inside the vegetation, but still good ground, no problem again with collecting ground DEMs from this model either. So if you look at this quantitatively with the Regal, we're seeing 31 points per meter squared on the ground. So this is not the point density in general, but it's point density of points that were classified as ground through an automatic ground classification algorithm in TrueView Evo. The 515, 43 points per meter squared on the ground, and then the 410, even the 410 is at 15 points per meter squared. So the take-home message out of all of this is any of these three sensors in this type of vegetation will do fine on collecting ground models. And what about vertical network accuracy? Again, we'll supply you with these slides, but it's the kind of progression that you would expect. With the Regal system, we have a root mean squared error of 1.6 centimeters. Again, 75 meter AGL. We're looking at all returns, overlapping flight lines, so we haven't called out any flight lines. And we've done no post-process geometric correction. So this is solely from the calibration of the LiDAR system. And we're looking at 24 checkpoints within the area that we've covered. So the Regal 1.6, the TrueView 515 coming in RMSE of 3.1 centimeters, and the 410 coming in at 3.5. So, you know, the Regal is just, you know, excellent performance as we would expect. It's got a bias of about 7 millimeters. So if you took the bias out, you'd have an RMSE that was around the 1 centimeter level. So quite good results from that sensor. Actually, not quite good. They're spectacular. Can you believe that thing was flying on a drone and achieved this kind of accuracy with no ground control? It's remarkable. And again, we've got a decision matrix on which sensor is appropriate for what. All right, so at this point, we'll turn it over to Madeline, who's going to go through a discussion of the business model of these these three members of the product family. Thank you.
Thanks, Louis. Can you hear me okay?
Yep, we can hear you good. And we can see your screen.
Let's see. Okie dokie. So today I'll be covering options related to acquiring the TrueView system. Our main goal when looking across the family of sensors is to offer a flexible solution to cover a wide range of customer needs. So let's discuss the packaging of our systems. When purchasing or subscribing to a TrueView system, you'll receive the components appearing on my slide. You'll select your sensor, either a 410, 515, 635, or 640. Each unit will be fully integrated with our dual 20 megapixel mapping cameras and a Planex position and orientation system. A control box for quick visual indicators when the system is ready for operation, antenna kit, a memory synchronization unit for quick data transfer from the LiDAR and cameras to a computer, 2 batteries, a battery charger, case, and 2 days of virtual training. Software is a critical item to consider when acquiring a UAV LiDAR system. We understand how complex LiDAR processing can be for new users. Our aim when creating the TrueView system was to create a full ecosystem to allow users the ability to do start-to-finish processing within our product. Our software takes users beyond creation of the true colorized point cloud, and it allows users to generate deliverables for their clients. Regardless of the business model you select, we include extensive software tools, making GeoCue a one-stop shop for hardware and software. The standard purchase and subscription model of our systems include licenses of TrueView Evo, PausPack, and the TrueView portal. When purchasing a unit, you'll receive a desktop version of PausPack, and when getting a subscription unit, you'll process your PausPack data in the cloud. GeoCue offers virtual training each month. We break the training up into 2 sessions, the first day covering pre-flight mission planning through colorization of the point cloud. The second day covers topics like classification and exporting DIMMs. We keep class sizes low to allow engagement during the training courses. Our spring classes are filling up fast, so please let us know if you need to reserve a spot. Outside of the provided kit, you'll need to select an airframe to mount the TrueView system on. We try to keep things simple when selecting an airframe. The TrueView system will mount to any platform capable of carrying the payload of the system. You'll also want to ensure the landing gear will not obstruct the view of the sensors. Our most common integration is on the DJI platforms. With a subscription unit, we include the mount for the M300 or M600 at no additional cost. For purchase systems, you can acquire a mount for an additional fee. If you opt to mount the TrueView on a non-DJI platform, we can provide integration on a consulting basis. We have integrated on numerous platforms to date. At GeoCue, we offer a wide variety of additional products that might be of interest to you. We're an enterprise DJI distributor. We offer base stations and rover kits through a company named iGauge, as well as customizable training and consulting services. Through our partnership and integration of the Applanix hardware in our system, we offer several different positioning options. Our recommended setup is using a physical base station on site. Other services include SmartBase and PPRTX. These can be utilized as needed, and fees are assessed by the minutes of flying time. We'll now cover costs associated with getting started. I've listed the cost for purchasing our systems on the screen. The TrueView 410 is priced at $55,000. The TrueView 515 is priced at $75,000. The TrueView 635 is priced at $164,000, and the TrueView 640 at $199,000. This includes the LiDAR sensor, cameras, software, and 2 days of training. It does not include the drone or base station equipment. For anyone interested, we do partner with a finance company who can characterize the cost of the TrueView system over 24 to 60 months. The first year of hardware and software maintenance is included with each purchase. Out-year maintenance on the system is listed on your screen. You have the option to select comprehensive software and hardware maintenance after the first year. You may also select to continue software-only maintenance and handle hardware issues on a case-by-case basis. Next, we'll cover our popular subscription option offered on our TrueView 410 and TrueView 515 models. All of our subscription units include 500 minutes of flying time in 1 month period. This allows for operations greater than 1,000 acres. If you exceed the amount of allotted time, additional minutes can be purchased. Our subscription offering on the 410 is priced just below $7,000 on a 1 month subscription. Our most popular option is the 3-month option, giving users ample time to conduct internal training on systems prior to deployment. The 3-month offering is priced at $14,850. The subscription systems include the sensors, software, mounting bracket for the M600 or M300, and 2 days of virtual training. Our subscription offering on the 515, the 1 month option is priced just below $8,000. And again, our most popular option on the 515 is probably the 3-month option. The 3-month option is priced at $17,000. Again, the 515 subscription system includes the sensor, software, mounting bracket for M600 or M300, and 2 days of virtual training. Maintenance for all subscription systems are included in the pricing, and all systems are kept up to date with respect to firmware and calibration. Hopefully today's presentation provided a broad overview of the sensors and software. We think of ourselves as technology consultants when engaging with our clients who are interested in our TrueView technology. We never guess at the solution that fits their needs. We evaluate accuracy requirements, project scope, and budget. This in-depth evaluation allows us to guide companies to a sensor that best fits their business. Our success is evident through the success of our customers. We've watched companies begin with our subscription model that now own purchase systems. We have companies with more work than a single system can support, creating the deployment of multiple systems. We hope you'll also trust us as your supplier of UAV LiDAR equipment. So with that, I'll conclude my portion of today's presentation. I really appreciate everyone joining us for the webinar today. We will have sample data available following today's session, so please contact us if you'd like a copy. In just a few moments, we'll also be launching a poll question. If you'd like to set up a discussion of the technology, please let us know by selecting your level of interest. So with that, I will hand it over to you, Martin, for some questions and also the poll question from Crystal.
Thank you, Madeline. Yeah, I'll go ahead and launch that poll question. And while that is open and live, Martin will go over our questions that we got in.
Great, thank you, Crystal. Yeah, I think we've handled most of the questions. A couple I'll just review because I think they're probably of general interest to the audience here. Just regarding the training, just to add a little bit of detail there, as has been mentioned, we include 2 days of training. Transitioning out of it being pure online training, of course, as things open up here. So the question is sort of how effective is that training? How quickly can you come up to speed with being proficient with operating the system? So I'll break that down into a couple of different areas. First of all, if you are already experienced flying drones, if you're doing photogrammetric type surveys and you or someone on your crew has a survey background, you can set up a base station, you're familiar with going out and doing a survey project, then the 2 days of training is really effective in getting you focused on the TrueView sensor setup, flight planning, data processing, and is very effective for getting you up and running and doing your own projects within that week of doing that training. Of course, there's a little bit of a learning curve, but generally we see most people that have that background, have some flight experience, have some survey background, they're up and independent, operating, not using our support desk very much within the first 3.5 dozen flights. It really is a very simplified workflow that really nicely eases you into being able to go out, plan a survey, execute a survey, process the data, and generate some product from that. The other area that does expand on that training a little bit, and I will just mention it because it comes up with almost all discussions we have with people, from the TrueView data, you're getting the point cloud, the obliques, the ortho imagery if you're running through that meta shape. Obviously, there's additional value add work that may need to be done to that. Very typical thing might be to do a digital train model or generate some contours off that data set. So there may be some additional training if you're not familiar with those workflows and those processes with LiDAR data that you may want to add on there. And we offer some additional paid training in those areas. For instance, if you want to do surface modeling or volumetrics, we can arrange training for those particular workflows and tool sets in TrueView Evo. So there may be a little bit of extra training on the value add or final product generation side you want to think about. But again, if you've got that background, that's going to come up very, very quickly. Typically within a couple of weeks of working on those tool sets, you'll be quite comfortable with doing that. Another question, just to clarify, we do get a lot of questions about the M300. Lewis mentioned this at the beginning. With the M300, you can carry both the 410 and the 515. The 635 and 640 will not work with the M300. The payloads are too heavy for that. Yeah, and I think that's all we've got here, Crystal. Just refresh, of course, we are recording this. You'll get a link to the recording. The slide presentation will be available. And as Madeline mentioned, there is sample data available. So if you're really interested in seeing some of this really nice data, just let us know. We've got 410, 515, 635, 645, 640 data sets all available for you. So
Awesome.
with that, I'll toss it back to you, Crystal.
Thank you, Martin, for going over that. And I just wanted to again thank Lewis, Madeline, and Martin for joining us on this webinar today. And thank you for everyone who registered and attended. We hope that everyone continues to stay healthy and safe, like Martin said. This is being recorded and we will distribute it to everyone registered. So thank you again for joining us, and we hope to hear from you soon.
All right. Thanks, everyone. Have a good day.